Professor, if you're talking, we can't hear you. You're on mute.
Well, I thought I was unmuted. I'm sorry. So let's go back and keep in mind when we look at a biogeochemical cycle, we're going to be looking at some material such as water, some chemical that moves through the bio, the living part of the environment, and the geo, the non-living part of the environment. So notice we can't study a biogeochemical cycle if we're just looking at a population, because populations only include living organisms of one species. We can't look at a biogeochemical cycle if we're only looking at a community, because that includes living organisms of different species, but it doesn't include the non-living environment. Now, the other thing we need to keep in mind is if we look at the flow of energy through our environment, the flow of energy is one way. Energy comes into our community as sunlight in most cases. There are some bacteria that can use other sources of energy. The energy gets transferred through the different trophic levels. Eventually, the energy, the biomass, ends up in decomposers. But it's a one-way path. In contrast, when we look at a biogeochemical cycle, remember when we talked about the Krebs cycle back in Biology 105? When we have a cycle, wherever we start, that's where we finish. So unlike energy flow, which is one way, this is in a sense a circular flow. We're going to have a starting point. We're going to go through various steps. We're going to end up back at that same starting point. Since it's a cycle, really the starting point you pick is somewhat arbitrary, because ultimately if we're anywhere on a circle, we're going to get back to our starting point if we follow our circle all the way around. But usually with chemicals, we think of the starting point as being how they tend to exist in nature. So if we look at the water cycle, at the temperatures that we find over most of the earth, most of the year, water is a liquid. It has to get relatively hot for water to vaporize, to boil, and it has to get relatively cold for water to freeze. So we typically think of water as being a liquid. So we're thinking of the water as starting out in oceans or maybe in fresh water in lakes like Lake Michigan or in rivers like the Chicago River or smaller streams. And whenever we have water or other liquids for that matter in contact with a gas, some molecules of the liquid will evaporate. So there's evaporation wherever liquid water and air come in contact. So this evaporation puts water into the atmosphere. Notice that the water that goes into the atmosphere is no longer liquid water, it's water vapor or water as a gas. So think of steam. Now, by the same token, notice that whenever we have air in contact with water, some of the air will diffuse back into the ocean and some of the water will condense back into the ocean. So, if you looked at the grass a few mornings ago, at least if you were early enough, you noticed frost on the grass. So this is water that condensed overnight when the temperature got lower. Where was the water before it condensed and formed this solid, very thin layer of ice? Well, it was water vapor that was in the air. When the weather gets warmer, it won't form frost, but you might get up in the morning and you might see dew on the grass. Or if you go walk outside with your dog or go out to get the newspaper and walk through the grass, your feet will get wet. That's from this dew, that's from this condensation. Now notice the water evaporating from the oceans and the lakes and the rivers and streams and the water that condenses back into those. is really in a dynamic equilibrium. So remember, we talked about a dynamic equilibrium back in 105 when we were talking about diffusion and osmosis. And in a dynamic equilibrium, we have molecules or atoms moving around randomly as they do, but the movements are equal in all directions. So there's really no changes in our situation. So what happens to this water that goes into the air? Because some of it condenses back onto the land or into the oceans or on top of a lake. But some of it stays in the atmosphere for a longer period of time and forms clouds. So when this water falls from these clouds back to the solid surface of the earth, to the ground, or back over water, this is called precipitation. Now, precipitation could return the water directly to an ocean or a lake or a river, in which case there's not really much to talk about. But if precipitation happens over land, it can still get back to an ocean or a lake or a river, but it takes a little bit longer. So if we look at precipitation, some precipitation falls at high levels in the mountains, and when the precipitation falls, it's snow. We get that down at the lower elevations too, and we can see the effects of snow. As long as the weather is cold, the ice remains, the water remains in a solid state, either ice or snow. But when it gets warm enough, that snow and ice melt. Now, if it's warm, we don't get ice to start with. The precipitation occurs as just rain, or maybe something in between, like sleet. But when we have liquid water on the land, there's a few things that can happen to that liquid water. If the ground isn't holding as much water as it can, then some of this water will sink into the ground. And when this water sinks into the ground, some of it is absorbed by plants. So they list this as plant uptake. But notice that plant uptake is just the water that's absorbed by roots. Now, this water may move through several types of living organisms before it eventually gets returned to an ocean. If you eat a plant, think about what happens if it's a plant like celery or oranges that have a lot of water in them. You're basically eating water that was absorbed by plants through their roots. However, plant roots don't absorb all the water that soaks into the ground. Some of the water that soaks into the ground, we say that it infiltrates and it goes deeper than the plant roots, and it forms something that we call groundwater. Now, if we look underground, there are certain rocks that are porous, that have small openings in them and water can flow through. So when we have water that falls to the ground as precipitation, and this water forms groundwater, it gradually flows back into around here, most likely Lake Michigan. But if you live closer to the coast, it could flow into the Atlantic Ocean, or if you live on the other side of the Rockies, it could flow into the Pacific Ocean. Now, notice, water evaporating from the oceans is very quick. Plants absorbing water from the soil by their roots, that's very fast. But groundwater is really, really incredibly slow. It can take thousands or hundreds of thousands. There's some evidence that it may even take millions of years for water that goes into the groundwater, say in the middle of Nebraska, to end up flowing into the Mississippi or the Gulf of Mexico, depending on exactly where we're looking. So some of these processes, and it's usually processes that involve simple chemical reactions or biological processes, when we look at cycles, processes that are just chemical reactions or involve living organisms tend to be very fast. Geological processes like groundwater flow tend to be very, very slow. We're talking about a scale of thousands or even millions of years versus minutes, seconds. So there's a big difference. So it takes a long time for this groundwater to get back into the ocean. Now, because this groundwater is in porous rocks and some of it is even in open cavities, caves underground, this means that potentially we can tap into this water. And this is what people are doing when they dig wells. Now, there is one problem with digging wells and tapping into this underground water. If we start taking water out of this groundwater source, if we start taking water out faster than it's being replaced by precipitation and infiltration, then we have a problem, because what that means is something that we call the water table. How far below the surface of the ground the water comes up, the water table starts to drop. And this is one of those environmental problems that you don't hear much about, but really in almost all parts of the world right now, people are removing water, either for drinking water, for washing water, different purposes, but they're removing water from the groundwater much faster than it's being replaced. You may have read in the news some areas that have had some droughts. There was a drought in very southern Africa, in the country that we call South Africa, from about 2012 to 2018. They've had a little more rain lately. But in 2018, there was a lot of concern that Cape Town, one of the large cities in South Africa, was actually going to run out of water because of the fact that they had taken so much water out of the groundwater. They didn't really have any source of fresh water. And basically they had to pipe in their fresh water from areas that were pretty far away. There's one of the provinces in India is going through something similar now. Their problem is complicated because of global warming. Global warming has changed precipitation patterns. And one of the things that's happened in many parts of the world is there's less snow falling in the mountains. Well, that might not seem like that big a deal, except if we look at the northern portion of India. The northern portion of India is where most of the rivers come down from the Himalaya mountains. And since there's less snowfall, those rivers bring less water down to the lowlands every year. And so there are several cities in India that have a population of over 1 million people that are potentially at risk of running out of water in the next 5 to 10 years, depending on what the precipitation patterns are. So when water falls over land, some of the water is absorbed by plant roots. Some of the water forms groundwater, but if it rains for an extended period of time, or even if it rains for a short time, but it rains really hard, it takes a while for water to soak into the soil to form groundwater. And if it rains really hard, the rain is coming down so hard, there's not time for it to soak into the ground. And in fact, the top layers of the soil will have as much water as they can hold until that water percolates further down. So what happens if that occurs? You've all seen what happens. It's called runoff. When it rains really hard and you look out, what do you see on your driveway after a while, or sometimes in the middle of your front yard? There's a little stream flowing. That's the runoff. That's water that wasn't absorbed by plant roots. It's coming down so fast or such a long period of time. The soil has all it can hold temporarily, so it flows on the surface. And these are the 3 basic things that can happen to water when it forms as precipitation over land. Now, all these sources of water eventually end up back in oceans or lakes or rivers. Um, and the runoff and the water that's captured by plants are returned relatively quickly. The groundwater takes thousands or millions of years. So this is one of those problems, as I say, that you don't hear much about because it's not very dramatic. But if you know anybody who lives in an area where they have a well, one of the consequences of this is people who dig or drill wells. Um, if you know somebody who lives in a rural area or someplace where there's not a reliable city source of water, um, if you dig a well today, that well has to be dug deeper than if you would have dug it 20 years ago or 50 years ago. Why? Because humans have taken so much water out of the groundwater, the water table is going down. So that's a potential problem that we face. And like a lot of other potential environmental problems, global warming is making it worse because global warming is changing precipitation patterns. And keep in mind, when we look at most large cities that people have built over the millennia, most large cities have been built near sources of water, even oceans where they could serve as harbors, but if not oceans, rivers like Chicago. Um, One of the reasons that Chicago became a big city in the 1800s was because this was kind of the western point of where goods were shipped through the Great Lakes. And also timber and farming goods could be picked up here in Chicago and shipped back east to the centers of population. So when we have changes in the pattern of rainfall, this can create a huge problem for people because of the way that we've built over the years. Now let's think about some cycles that involve single elements. So let's look at the carbon cycle. And when we think about the carbon cycle, we said with the water cycle, we typically think of the water cycle as starting with liquid water because at normal temperatures over most of the year on this planet, water is a liquid. With carbon, we typically think of the carbon cycle as starting with carbon dioxide in the atmosphere. Now, remember what we said about water in the ocean and water vapor a few minutes ago, that when we have a liquid in contact with air, there's diffusion across the two surfaces. So when we have carbon dioxide in the atmosphere, some carbon dioxide will diffuse into the water. Carbon dioxide that's in the water diffuses back into the air. And again, there's typically an equilibrium between these processes under normal circumstances. The carbon dioxide that diffuses into the water, some of it is used by plants. Remember, carbon dioxide is one of the reactants for photosynthesis. Some of the carbon dioxide that diffuses out of the water is produced by, they show fish, but remember, plants, algae, things like that also carry out aerobic cell respiration. And carbon dioxide is one of the products of that. Now, like with water, there are other ways that carbon dioxide can either leave the air or enter the air. So carbon dioxide can be removed from the air by photosynthesis. CO2 is the reactant in the light-independent reactions, if you recall. And once this carbon dioxide is removed from the air, then it's gradually returned by aerobic cell respiration, either by plants or by consumers like herbivores or the carnivores that eat them or the decomposers that eat everything. But remember what we said the other day. When herbivores eat plants, they don't eat all of the plants. So when plants die or when consumers die or even when decomposers die, some of their bodies are decomposed and the decomposers release more carbon dioxide back into the air. But some living organisms die under circumstances where they don't decompose very well. A lot of the bacteria that are decomposers, their cells carry out aerobic cell respiration, just like your cells do. Now, they don't have mitochondria. They do it a little bit differently, but they carry out aerobic cell respiration. So one of the reactants of aerobic cell respiration is oxygen. That's what the aerobic refers to. So for these organisms, for these decomposers, bacteria, fungi, protists, to effectively decompose something, they have to have a supply of oxygen. Sometimes living organisms die in environments where there's not that much oxygen. In a lot of swamps and marshes and bogs, when living organisms die, they fall into the water, and the water in most swamps and marshes and bogs is very stagnant. And because it's very stagnant, and because living organisms are constantly dying and falling into it, the oxygen levels are very low in the water in swamps and bogs. Why? Because living organisms have been falling into this water. The bacteria that decompose them use up the oxygen, and the bacteria use up the oxygen faster than it diffuses into the water. So oxygen levels are really low, which means if you die in a swamp or a bog, the body may not decompose for a long period of time. Why? Because there's not enough oxygen in the water for the bacteria and the protists and the fungi to decompose the body very rapidly. Besides areas like that, this often happens in the ocean. When living organisms die, living organisms in the ocean are either drifting with the current or they're swimming. When they die, either way, they quit drifting with the current, they quit swimming, they sink to the bottom. At the very bottom levels of the ocean, oxygen levels are very low. Why? Well, mostly because the very bottom levels of the ocean are so far away from the surface. Remember, oxygen would be diffusing in from the surface, just like carbon dioxide is. And if we're talking about a mile underneath the surface, now that oxygen has to diffuse a mile down to reach the lower surface. And there are some parts of the ocean deeper than a mile. So where we have low levels of oxygen, when organisms die, they don't necessarily decompose. Now, since they have lots of organic materials, organic compounds in them, over long periods of time, their bodies can be squished and compressed, squeezed, and their bodies can form oil and coal and natural gas, as well as some other things like peat. But these are the things that we typically refer to as fossil fuels. Keep in mind that, we use them as fuels, but they were produced long before humans came on the scene. Now, if we think about what happened before humans got here, keep in mind that it takes millions of years of these organic compounds being underground and being under the pressure of all the soil that's deposited on top of them. It takes millions of years for their bodies to be compressed enough to form oil or coal or gas. And one of the things that's cool, by the way, when you study coal or when you look at oil, you can sometimes find portions of organisms that aren't completely compressed. Most of the organic material in oil and coal and natural gas appears to come from plants, but you can sometimes find outlines of seeds and outlines of leaves and things like that. So you can actually tell sometimes what types of plants make up this material. Now, if humans don't intervene, then what we see is for all the carbon that's stored in this oil and coal and natural gas, for all of that to return to the air, it's going to take millions of years. First of all, it takes millions of years for oil and coal and natural gas to be formed. But now what has to happen is a geological process called erosion. Imagine that it rains a lot in this area. The rain eats little gullies into the ground. Eventually, the rain can eat gullies deep enough that it exposes some of this oil and coal and natural gas. And when that happens, when these are exposed to the air, they can oxidize, which is just the nice chemical name for saying they can start burning. Without anybody setting a match to them, they can start burning on their own. I haven't heard about it in a few years, but there's an area out in Tinley Park. I think now that Tinley is getting a little more developed, they've kind of taken care of this area. But used to be that once every 2 or 3 years, there would be a very low grade fire that would start out there because it was mostly decaying organic material. And there would be a lightning strike or something like that that would begin things burning. And then this is a natural fuel. So it would burn when Tinley was kind of small and there wasn't anything out there. I think they just used to let it burn, but now they want to take care of that because they've got big business and everything now. So notice, similar to the water cycle, this diffusion in and out of the air of carbon dioxide is very fast. Aerobic cell respiration, photosynthesis are very fast. These are biological processes. Remember what we said with the water cycle. Chemical reactions and biological processes are very quick. Geological processes are slow. Forming oil and coal and natural gas takes millions of years. Exposing those to the surface of the earth, at least without human intervention, takes millions of years. So these processes are very, very slow. Now, we'll come back to the carbon cycle in the next section when we talk about the biosphere. One of the global environmental problems that you've heard about is something called global warming. And global warming is really happening. One of the main reasons is because people are disrupting the carbon cycle. And that's where these factories and fossil fuel emissions come in. But we'll look at that when we talk about the biosphere. Let's look at some more biogeochemical cycles for now. So let's think about the nitrogen cycle. And probably the most notable thing about the nitrogen cycle is if we look at air, air is about 78% N2. So if you could take a handful of air, you could count all the molecules. About 78 of those molecules would be N2. About 21 of those molecules would be O2. So 78, 21. So nitrogen gas and oxygen gas account for about 99% of the gases, the molecules in the atmosphere around us. The third most common gas is argon. So we want to keep this in mind because later I mentioned we'll talk about global warming. And one of the things that's causing global warming is an increase in the amount of carbon dioxide in the air. But notice that carbon dioxide only makes up actually less than 1/10 of 1% of the gases. But despite the fact there's not a lot of it, it still is causing global warming. Now, there's a big problem for living organisms, which we've mentioned once or twice already this semester. Most living organisms can't use N2. They simply have no way to access it. You could put a plant in a room full of N2, and there's no way it would be able to use that N2 if it was just that plant by itself. However, there is a process called nitrogen fixation, and we have nitrogen fixing bacteria. Some of them live in plant roots, and bacteria can take N2 and they can convert N2 to ammonium, and depending on the type of bacteria, sometimes to nitrite and nitrate. Now notice ammonium by itself and nitrite by itself and nitrate by itself are not organic molecules, because remember, organic molecules have to contain carbon. So these have to be combined with something else to actually be an organic molecule. So these bacteria can take N2 and they can convert it to ammonium, or they convert it to nitrite or nitrate. Some of these bacteria live in the soil. Some of these bacteria are associated with the roots of plants. In particular, legumes, things like beans have legumes. But if we look at them, this also includes some plants like alfalfa. And plants that are legumes that have these bacteria in their root nodules, typically they're very high in protein. Beans are a good source of protein. Um, so this is one of the main ways that we get nitrogen. There are also a few fungi that can fix nitrogen. Notice this process is called nitrogen fixing or nitrogen fixation. So you don't want to think of this in terms of the nitrogen is broken. When we talk about nitrogen fixation, a gas fixation, we're talking about changing that from a gas to a solid or a liquid. So if we go back for a moment to the carbon cycle, when plants take carbon dioxide out of the air and use it to make organic compounds in photosynthesis, this is called carbon fixation. So this refers to changing a gas into either a liquid or a solid chemical. Now, when plants die, or not just plants, animals, protista, fungi, other decomposers, whatever we're talking about, bacteria, when living organisms die, bacteria, which is mostly the main decomposers, but fungi, and there are actually a few protistans that do this, and there are actually a few animals that do this. Some things like earthworms are partly decomposers. They can take the nitrogen compounds that are found in plants, and they can convert those to ammonium, and then they can convert that to nitrite, and then to nitrate. And then there are denitrifying bacteria. Denitrifying bacteria do the reverse of nitrogen fixation. They take nitrogen from nitrates and put them back into the atmosphere. Now, when the decomposers break down nitrogen-containing compounds to ammonium, to nitrite, to nitrate, then these can be reabsorbed by plant roots. So they could either be reabsorbed by plant roots, or they could ultimately be used by denitrifying bacteria. So, where do the decomposers get these nitrogen compounds? Well, remember, amino acids, that amine group is NH2, so that contains nitrogen. So anything built from amino acids like proteins has nitrogen in it. Even though the name is phospholipids have nitrogen in it. There are some things like the bacteria cell wall that are a combination of carbohydrate and amino acids. Remember that DNA and RNA have that thymine, cytosine, guanine, uracil. Those all contain nitrogen. So there are lots of nitrogen containing compounds in living organisms. ATP and ADP, I guess that's obvious since they're built from RNA. So we have lots of nitrogen containing compounds. Now, nitrogen is crucial because it's found in ADP and ATP, because it's found in DNA and RNA, because it's found in proteins. Nitrogen, if we look at various soils around the world, nitrogen is one of the 3 nutrients that's most often missing that limits plant growth. Along with nitrogen, potassium can be important. And along with nitrogen and potassium, the third one that's usually important is phosphorus. So when you look at a lot of fertilizers and you look at kind of their abbreviation for what the ingredients are, they list three numbers at the somewhere, 5, 10, 5. And this is the percentage of nitrogen, phosphorus, and potassium that they have. These aren't always the things that limit plant growth, but they are in most environments. So these are the three things that are most commonly put in commercial fertilizers. Now notice, since living organisms don't digest everything that they eat, a rich source of nitrogen compounds is feces. So feces in one form or another are often used as fertilizer as well. One of the types of feces that's used most often is guano, and guano is really bat feces. So you can actually get a job where you get paid to go into caves and scoop up bat poop, you know, if you're into that sort of thing. So let's look at the phosphorus cycle. But before we do, let's go back here for a moment. Notice that these are all biological processes. So this tells us that the nitrogen cycle is actually very rapid. So we want to keep that in mind. Unlike the cycles we've talked about before, notice we don't really have any geological processes shown here. So let's look at the phosphorus cycle. And the phosphorus cycle, we're going to see, at least in one way, is the opposite of the nitrogen cycle. Because in the phosphorus cycle, the geological processes are so slow, they make this whole cycle very slow. And that's also why phosphorus is relatively rare in a lot of environments. So if we look at phosphorus, and again, if you think about where phosphorus is found, ATP, ADP, cyclic AMP, remember those are triphosphate, diphosphate, monophosphate. DNA has a phosphate group, RNA has a phosphate group, phospholipids have a phosphate group. So those are some of the more common ones, but again, phosphate is a very important element. When we look at phosphorus, if we look out in nature, what we see is that phosphorus is typically found as what's called a polyatomic ion, a phosphate group. And a phosphate group has the chemical formula PO4, and it has a charge of -3. It's ionic. And because it has a charge, what we find in nature is that things that have positive or negative charges rarely exist by themselves, because if they have a positive or negative charge, that makes them very reactive. So phosphates react with a lot of positive ions. And when they react with positive ions, most of the phosphate compounds are not soluble in water. And since they're not soluble in water, this means that they precipitate. They form solid compounds. Basically, the compounds they form are different rocks and minerals. Now, these rocks and minerals, once they're formed, don't dissolve in water. If it's an area where there's a lot of acid rain, that can help to dissolve them. But if we're not in an area with a lot of acid rain, then these phosphate-containing rocks don't dissolve. So similar to when we talked about the carbon cycle, notice this is a chemical reaction for the phosphate group to react with something like, say, calcium, and then form a precipitate. But the process where this precipitated solid phosphate in the rock, where this is exposed to the air and gets weathered, which basically means little small pieces of it break off, that can take, again, thousands or millions of years. And in the phosphate cycle, this part of the cycle takes so much longer than the other steps that, again, phosphorus is very frequently a chemical element that limits plant growth in most environments. So again, this is why it's often found in fertilizer. Now, in living organisms, basically what we see is that phosphates can be absorbed by plants. When they're absorbed by plants, they're put into organic compounds like DNA, RNA, ATP, ADP. Animals get their phosphorus by eating plants. Notice that when you eat a plant, if those plant cells have some ATP in them, remember what we said about digestion, you don't get that ATP directly. You have to break it down into small molecules, absorb those into your body, and then rebuild your own ATP, even if it's exactly the same as the ATP you just ate. Then when living organisms die, they form detritus, which is just another name for this is what their bodies make when they fall apart. This is what's left of them. And this detritus is eaten by detrivores, which is just another name for decomposers. So what do these decomposers do? They produce plain phosphates. They isolate the phosphate groups from the ATP, from the DNA, from the phospholipids. The main thing that decomposers do is break down organic materials into simpler molecules. And then two different things can happen to these phosphates. They can either be absorbed by plant roots, or they can go into solution, react with a calcium atom or a magnesium atom or other types of atoms as well, and form a solid and enter the long phase of the cycle. So keep in mind, these are just a few examples of biogeochemical cycles. If we had the time, we could go through, there's a sulfur cycle. There's a cycle for literally all the elements that are found in living organisms. Out of the different organisms that out of the different elements that you might see on the periodic table, there are only about 40 of them that are found in living organisms, and most living organisms only have about 30. There are a few of the elements that are found here and there in kind of just an occasional organism, but not too many. But there are about 30 elements that are found in almost all living things. So keep in mind, though, no matter how many elements are found in most living things, if you think of Cheops, it always sounds to me like it should be an Egyptian pharaoh's name, but Cheops: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Those 6 elements in most living organisms make up more than half of their body weight. There's a few weird exceptions, like we're a weird exception because of bones. So we happen to have a lot more calcium than most living things do. But those 6 elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, that's the bulk of the body weight in most living organisms. Are there any questions about biogeochemical cycles for now? Okay, if not, I will let you go for the weekend. We won't have any questions posted for a few days till we finish with ecology. We'll probably have one small assignment next week, similar to what we've been having. Keep in mind, if you're thinking about dropping, next Monday is the last day to withdraw from class. If you're thinking about dropping, make sure you check the grades online, because all the grades are posted at this point, so you can see what your average is right now if you'd like to see. If you want to have a Zoom meeting over the weekend and talk, or whatever, send me an email, or we can just discuss things by email. But keep in mind, usually I tell people that the best prediction for what your grade is going to be at the end of the semester is to look at what your average is now. Might go up or down a little bit. If you're right on the borderline, 89 or 91, your grade might change. But if you're kind of in the middle, 75 or 85 or whatever, the odds are probably pretty good your grade won't change at this point. But double check your grades. I'll remind you again on Monday. I'm not trying to talk you into withdrawing, but I don't want anybody who wants to withdraw to miss a chance. My advice would be, if you have a C or better, I would recommend staying in the class, because even if a C is not the grade you want to get, If you have a C or better, that will usually give you what you need if you want to move on and take anatomy and physiology or microbiology. And if you just withdraw from the class, you'll have to wait until you get that C probably to take some of the more advanced courses that you might be interested in. But other than that, enjoy the weekend. And for once, there's no assignment to work on over the weekend.